Hello. So now we will move further in the chapter of force convection. So we will move forward on the topic of force convection at external flow. Right. So we have introduced till now about the basic convection and the governing law of the convection heat transfer, that is Newton's law of cooling. So before going into the convection, we should have some background about the fluid mechanics. So let me give you some background about the fluid mechanics here, about the hydrodynamic boundary layer. So first of all, let's jot down the assumptions here about this hydrodynamic boundary layer development, that is incompressible flow. Fluid means the Mach number is less than 0.3, right? And steady state means the properties like fluid velocity and the pressures, densities are not changing with respect to time. So nothing is changing with respect to time, right? And flow is parallel to the surface, right? These are the assumptions, underlying assumptions about this boundary layer concept. So first, let's consider the ambient fluid which is having velocity u infinity, flows over a stationary flat plate. This is a stationary flat plate. Right? So when the first fluid layer, which is this, comes in contact with the wall, if we just zoom in, it will adhere to the wall. This is called adhesion, right? And this layer will have the same velocity as the plate. Here plate is stationary, so fluid will have zero velocity, right? This is also called no slip boundary condition. So because of adhesion and friction of the surface, the fluid layer which is in immediate contact with the wall comes to immediate rest, right? So it means at y is equal to 0, velocity of the fluid is 0. This is called no slip boundary condition. So when adjacent layer, the layer which is above it, this stationary layer, try to move the red layer which is in immediate contact with the wall, which has brought to rest by the wall, try to retard this green layer, right? As a result, the friction is entered into the fluid layers and the presence of plate is felt by these adjacent layers, and fluid motion will be retarded along the length of the plate. Alright, so the distance up to which the presence of plate is felt is known as the boundary layer thickness, right? So This is a rough sense or layman language definition. So this phenomena of entering the friction in the fluid layers is continued across the layer, right, like this, and the thin region is formed on the top of the plate, in which velocity gradients are very much significant. Alright, so this is known as hydrodynamic boundary layer region. So this region is known as hydrodynamic boundary layer region. So, but there exists one edge which will distinguish the fluid motion into two regions, more specifically. The region which is having higher, relatively very high velocity gradients, which are near to the wall, where viscous effect of the fluids are predominant. These are called hydrodynamic region, and the region which is outside this viscous region, which don't have or nearly zero velocity gradients, right? So the edge which will differentiate between these two regions is known as the edge of boundary layer, right? Moreover, when these fluid layers are moving over the surface, they exert shear and pressure forces on the surface. So on the surface, shear and pressure forces are applied by this fluid motion, and there exists a resultant force, and the horizontal component of this resultant force is known as the drag force, and the drag force per unit area is known as shear stress, right? So let me write it in terms of expressions. So drag force per unit area is the shear stress, which is nothing but the wall shear stress. Wall shear stress we can find if we know the velocity gradient at the wall, u by uy at y is equal to 0 at the wall. Moreover, wall shear stress can also be found from the non-dimensional coefficients, which is nothing but the friction coefficient. Skin friction. Coefficient, right? So the main aim of studying this hydrodynamic boundary layer theory is to find this shear stress, right? So if we just look more deeply into this boundary layer concept, the location, that is the leading edge, here the whole fluid is having the same velocity as u infinity, except the first layer. So velocity is very sharply changing from 0 to u infinity. It means the velocity gradients are highest at this point, and these velocity gradients will further reduces as we move along the length of the plate, because more and more fluid will feel the presence of the plate. It means more and more fluid will become retarded by the friction of the plate, right? So velocity stresses start to decrease along the length. Alright, so near this region, leading edge, if we find the velocity gradient, so it will be, it can be, velocity profile is like very much linear, more or less linear only here, and will be changing from u infinity infinity minus 0 at the wall, and the thickness will be very very small. So that's why the velocity gradients are highest at the leading edge. So as we can see from this expression, that as delta increases, which is the case here, that as we are moving along the length of the plate, delta is increasing, right? So delta increases, velocity gradients decreases, it means fall shear stress will also decrease. The highest shear occur at the leading edge of the plate. Moreover, if we increase the flow velocity, the velocity gradients are going to increase, right? So the drag force will also increases. There are some non-dimensional numbers which I am going to introduce here. First is Reynolds number, which is nothing but the inertia force divided by the viscous force. We can find this from the rho times velocity of the fluid, reference velocity of the fluid, times characteristic length divided by viscosity of the fluid. Here, this UF is the reference velocity, which is undisturbed fluid velocity. So for a flow over a flat plate, we can define based on this Reynolds number that if the flow is laminar or turbulent. For flow over a flat plate, if Reynolds number is less than 10 power 5 times 10 power 5, it is laminar, and if it is greater than 10 power 7, it is turbulent flow. Right, and also there are some analytical expressions for the boundary layer thickness for laminar flow and turbulent flow. For laminar flow, it is 5 times x divided by Reynolds number x. If you expand it, this is local Reynolds number. It means Reynolds number at particular location, right? So if they expand it, that the boundary layer thickness will come out to be square root of x. That's why that edge of the boundary layer was like this, square root of this x, right? Similarly, for turbulent flow, it is 0.358 x divided by Reynolds number power 1 by 5. And if we want to find the screen friction coefficient, it can be found as 0.664 divided by Reynolds number under root x. And for turbulent flow, it is 0.06 divided by Reynolds number power 1 by 5. Right, and how we will find its characteristic length? Suppose this is the flat plate. In the case of Reynolds number